So from ideal gas equation, PV equal to ideal gas equation, PV equal to N R from nRT. From this ideal gas equation, PV is equal to nRT. From this, R value also can be calculated for any given gas. So the volume of, already we know that the volume of 1 mole of gas, ideal gas, occupy the volume is how much? 22.7 liters. The V is 22.7 liters at STP conditions, already we know. And temperature is 273.15 Kelvin. The pressure is 1 bar pressure. So for 1 mole of ideal gas, the R can be calculated. R, universal gas constant, can be calculated. 1 bar is equal to 10 to the power of 5 pascals into 22.7 into 10 to the power of minus 3 meter cube, convert into meter cube. 1 mole upon 1 mole, 273.15 Kelvin temperature. Then we can get the value is 8.314 pascals per meter cube, pascals meter cube per Kelvin per mole we can get. The value of R is, universal gas constant, is 8.314, and in terms of bars, 8.314 into 10 to the power of minus 2 bars liter per Kelvin per mole, and in terms of joules, 8.314 joules per Kelvin per mole. So this is the value of R, universal gas constant. Value is how much? Means 8.314. 4 is the value. From the ideal gas equation, a relationship between 4 variables. So yes, 4 variables. Out of 4 variables, if you know 3, and fourth one can be easily calculated. And also sometimes if the temperature is kept, temperature, volume, pressure for the fixed amount of gas known is T1, B1 and P1, and change it to T2, V2 and P2, then we have to use the combined equation, gas equation, P1 upon V1 upon T1 equal to P2 into V2 upon T2. So by using this equation, we can find out any variable. That means out of the 6 variables, this is, for example, if you want to find out T2, then we must know P1, V1, T1, P2, V2, then we'll calculate the T2. This is called combined ideal gas equation. Combined ideal gas equation, we say. So next is the topic about Dalton's law of partial pressures. Dalton's law of partial pressures. Look at this picture. There are 5 cylinders containing individual gases. One is oxygen, nitrogen, argon, water, and carbon dioxide, water vapor. So these are the 5 gases having the individual pressures. So these pressures are different. These individual pressures are different. Okay. And there is another cylinder containing air, mixture of non-reacting gases. Mixture of all these gases, oxygen, nitrogen, argon, water vapor, carbon dioxide present in this cylinder. And look at this gas pressure. This gaseous pressure reading is more. That means the air pressure is greater than the individual gases partial pressures, we say. That means the air pressure, the pressure exerted by this mixture of non-reacting gases is always greater than the individual gas pressures. Individual gas pressures, we say. So for the fixed moles for the fixed moles and that fixed volume at the given temperature. This law was formulated. What is that Dalton's law of partial pressure talks about? Means the pressure, the total pressure exerted by this is total pressure exerted by, that is PT, the total pressure exerted by the non-reactive mixture of the gases is equal to sum of the partial pressures of the individual gases present in that at given temperature and for the fixed volume of the gases. Again, I'm repeating the Dalton's law partial pressure statement. So what this Dalton's law partial pressures talks about? The total pressure exerted by the mixture of non-reacting gases is equal to sum of the partial pressures of individual gases. That means PT is the total pressure, which is equal to P1 is the partial pressure plus P2 is the partial pressure of second component plus P3 is the third component. The sum of the partial pressures of the individual gases is equal to the total pressure of the non-reactive gases is called the Dalton's law of partial pressures, we say. That means in the mixture of gases, the pressure exerted by individual gas is called the partial pressure, we say. What is the partial pressure means? In the total mixture of the gases, the pressure exerted by the individual gas is said to be partial pressure, we say. Mathematically, P total is equal to P1 plus P2 plus P3. Mathematically, so this is the formula we can get at given constant temperature, constant volume, where the P total is the total pressure exerted by the mixture of gases, we say P1, P2 and P3 etc. are the partial pressure of the gases. So, but how we get these partial pressures of the gases means the partial pressure of the gases, the dry gas can be calculated by subtracting the vapor pressure of the water from the total pressure of the moist, which contain water vapor also. Actually, the dry gas mostly collected from the surface of the water. So from the surface of the water, hence, so along with the pressure of the dry gas, we can get the water vapor, so pressure also we can get. Hence, the dry gas, the partial pressure applied by the partial pressure of the dry gas can be obtained from the total pressure of the gases minus aqueous tension, water vapor, so pressure. We can get the partial pressure of the dry gas we can get. The partial pressure in terms of mole fraction, suppose at the temperature T, 3 gases enclosed in the volume P1. Okay, now the partial pressures is P1, P2 and P3 respectively. Then, so we can instead of this P1, P2, we take them in the form of ABC. Consider a mixture of non-reactive gases ABC. ABC you can take, assume that these ABC now non-reactive mixture of gases ABC are present in the cylinder consisting of the manometer. This is the manometer. In the cylinder, gas A is present, gas B is present. Other one is C is also present in this non-reactive mixture of the gas are present in the cylinder. There is a manometer is fixed here. This manometer will show the P total pressure of the gases present in this cylinder. And so now the partial pressure exerted by each one can be calculated by ideal gas equation PV equal to nRT. So now the P total is the pressure shown by ABC non-reactive mixture of the gases. But inside the cylinder, each gas has its own partial pressure. One is PA, partial pressure exerted by A component. Other one is PB, and the other one is PC, partial pressure applied by the C component. Now here we have to use ideal gas equation PV equal to nRT to get the partial pressures of the gases, partial pressure of the gases. For example, partial pressure exerted by PA component is equal to its number of moles Na. R is a constant, T is the constant temperature, V is the volume, constant volume. Similarly, PB also partial pressure exerted by the PB component equal to NB upon R into T upon V. The partial pressure exerted by the C component is equal to its number of moles Nc RT upon V. And where Na, B and Nc are number of moles of the gases A, B, C respectively. By Dalton's law, partial pressure P total means total pressure is equal to sum of the partial pressure of A component, B component and C component. We can write this equation P total is equal to number of moles of A component RT upon V plus NB RT upon V NC RT upon. If you take common this RT upon V, because since it is a constant, P total is equal to RT upon V Na plus NB plus, so sum of the moles. Now, so therefore the partial pressure is divided by P total divided by the P total here. This is the P total. So now we can get number of moles of A component RT upon V by RT upon V. So total number of moles of the mixture. So RT upon V and RT upon V is cancelled. Then we get which is equal to Na number of moles of A component total number of moles which is equal to N. Sum of these number of moles of A, B, C equal to N. That means this is the total moles. This is total moles of the mixture. This is and only moles of this A component. The ratio of number of moles of A component upon the total to the total moles of that mixture is equal to what we call, already we know this is mole fraction of A. That means from this what we can understand is that the partial pressure of A component to the total moles is equal to mole fraction of A component. This is. That means the mole fraction of A component increases, its partial pressure increases from the total of the pressures. So then mole fraction partial pressure of A component is equal to, here we can write this equation PA is equal to its mole fraction how much XA into P total. We can write P total. That means the partial pressure of any component in the non-reacting mixture is directly proportional to its mole fraction. That is the relationship between mole fraction and partial pressures. Similarly, we can write equation. PB partial pressure of the B component is equal to XB. Its mole fraction is XB to the multiplied with the P total. This is, and similarly partial pressure of C component also PC is equal to its mole fraction is, we can write XC PT multiplied with the PT, P total we say. So that means this is a relationship between mole fraction versus the partial pressures from the Dalton's law. We say the partial pressure, now we can make the statement the partial pressure is equal to mole fraction into total pressure of the non-reactive gases. This is the relationship between partial pressure and mole fraction of the gas. So this is John Dalton's law of partial pressure, we say. Now coming for the discussion about the kinetic molecular theory of gases. So if you want to learn about kinetic molecular theory of gases, actually why this kinetic